The Big Bang did not bang. There was no explosion, no sudden burst of light and matter into nothingness. The defining moment of our universe, the very event we named for its supposed explosive nature, was silent. And that silence speaks volumes about the greatest misconception in our collective understanding of existence. You've been told a story, a convenient narrative packaged into textbooks and documentaries, but the universe doesn't care about our stories. It harbors secrets in its geometry that defy our intuition, mock our perception, and render our most sophisticated mathematics as primitive scribbles on a cosmic cave wall. Look up at the night sky. What do you see? Stars scattered across a vast emptiness? Galaxies drifting away from each other into an infinite void? Your eyes, remarkable as they are lying to you. The universe you perceive isn't just stranger than you imagine. It's stranger than you can imagine. The shape of our universe may be the greatest riddle ever posed, and we're not just unsure of the answer. We're unsure if an answer even exists, in a form we could comprehend. What if the universe has no edge, yet remains finite? What if straight doesn't exist, and every path you could possibly travel eventually brings you back to where you started? What if the 3 dimensions you've navigated your entire life are merely shadows cast by higher dimensions you can never perceive? If you could somehow step outside of the universe, an impossibility that nonetheless helps us visualize, what would you see? A sphere? A saddle? A vast, incomprehensible origami of space-time? Or something so alien to human conception that our languages lack the vocabulary to describe it? Picture this. You're standing on the surface of the Earth. Walk in any direction long enough, and you'll eventually return to your starting point. Not because you've reached an edge and turned around, but because the very geometry of the Earth's surface curves back upon itself. The universe may be playing this same trick, but in higher dimensions that render our everyday perception useless. The universe we inhabit might be flat. It might be positively curved like a hypersphere. It might be negatively curved like a cosmic saddle. Each possibility creates a fundamentally different reality with profound implications for our past and future. And here's the unsettling truth. We don't know which one is correct. Our most advanced telescopes have peered to the edge of the observable universe, and still, the answer eludes us. When astronomers say the universe is expanding, what exactly is it expanding into? Nothing. There is no outside for the universe to expand into. Space itself is stretching, creating more of itself from itself, like a rubber sheet being pulled from all directions simultaneously. Your intuition rebels against this concept. Because you've evolved to understand the movement of objects through space, not the expansion of space itself. Let's rewind time in your mind, billions of years backward. Galaxies rush toward each other, stars uncollapse, matter compresses. As you approach the beginning, you expect to see a singular point, the cosmic egg from which everything hatched. But what if there was no beginning? Point? What if, like a video played in reverse that never reaches its first frame, the universe simply becomes denser and hotter without ever converging to a singularity? What if the Big Bang was not the beginning, but merely a phase transition? In an eternal cosmos, the universe may be shaped like a torus, a cosmic donut. Travel far enough in one direction, and you'll return to your starting point from the opposite side. In such a universe, if you looked far enough through a powerful enough telescope, you might see the back of your own head, as light from Earth completed a journey around the entire universe. Or perhaps our universe is just one bubble in a vast, foaming sea of universes, each with its own physics, its own dimensions, its own notion of time. In this multiverse, our understanding of shape becomes even more limited, like bacteria in a petri dish contemplating the laboratory that contains them. What if space has tiny, curled-up dimensions at every point? Dimensions so small we can't detect them, yet vital to the fundamental forces that govern reality. String theory suggests exactly this, that beneath the three dimensions we perceive lie several more, coiled up like tightly wound scrolls at every point in space. You may wonder why this matters, why the shape of something so vast should concern creatures so small. But the geometry of our universe dictates everything: how galaxies form, how light travels, how gravity behaves, and ultimately, how our story ends. In a flat universe, expansion continues forever, leading to a cold, dark eternity as stars burn out one by one. In a closed universe, expansion eventually reverses, leading to a big crunch as all matter collapses back together. In an open universe, expansion accelerates, potentially ripping apart the very fabric of reality. In a big rip, the universe doesn't just contain paradoxes, it is a paradox. Invisible dark energy pushes galaxies apart with increasing speed, while equally invisible dark matter holds galaxies together. Together, these unseen forces compose over 95% of everything that exists. We are minority shareholders in reality, blind to most of what constitutes our cosmos. As you contemplate these possibilities, remember that you are not separate from this cosmic puzzle. You are part of it. The atoms in your body were forged in the hearts of dying stars. The shape of the universe is, in some sense, your shape. Its mysteries are your mysteries. The truth about our universe's shape lies in the subtle patterns of microwave radiation left over from the earliest moments after the Big Bang, the cosmic microwave background. Like detectives analyzing the echo of an ancient explosion, cosmologists scrutinize this radiation for clues about the geometry of spacetime. The patterns we've observed so far suggest a universe that is remarkably flat, but with a margin of error that leaves room for curvature on scales beyond our current ability to measure. What if the true shape of the universe is fundamentally unknowable to beings like us, creatures who evolved to navigate the savannah, not to comprehend cosmic geometry? What if we're like the proverbial blind men touching different parts of an elephant, each convinced we understand the whole based on the small part we can grasp? This is not just a scientific question, but a philosophical one, a theological one, an existential one. In seeking the shape of the universe, we are really asking, what is our place within it? Are we significant or insignificant? Are we accidental or inevitable? Are we alone? The most profound question may not be what shape the E2 universe is, but why it has any shape at all. Why does anything exist rather than nothing? This question haunts the edges of cosmology, where science meets philosophy in the shadowlands of human understanding. So as we begin this journey together, this exploration of cosmic geometry and ultimate reality, prepare to have your perception not just challenged, but fundamentally reconstructed. The universe is not just stranger than we suppose, but stranger than we can suppose. And in that strangeness lies the most beautiful mystery of all. For nearly a century, cosmologists have told us the universe is expanding. This isn't speculation, it's observable fact. Everywhere we look, galaxies drift away from each other like embers scattered from a cosmic fire, their light stretched into redness as space itself unfurls between them. This expansion creates a map of time and space so vast that your mind evolved to track predators across savannas and remember the locations of seasonal fruit, buckles under its immensity. But what if this expansion, this fundamental truth of modern astronomy, is actually showing us something far stranger about the shape of reality itself? When Edwin Hubble first discovered this universal expansion in the 1920s, he glimpsed only the surface of a profound mystery. The galaxies aren't moving through space like ships on a cosmic ocean. Space itself is stretching. Imagine ants painted on the surface of a balloon. As the balloon inflates, the ants don't move, but the distances between them increase. This is our universe. Not objects moving through space, but space itself dilating, creating more of itself between every star, planet, and atom. But this raises an immediate contradiction. If everything is moving away from everything else, then everything must have once been together. Rewind the cosmic film far enough, and all matter and energy in the observable universe compresses into a state of infinite density, the singularity from which the Big Bang emerged. At least, that's what we've been taught. The early universe wasn't just hot, it was a furnace where time itself was still learning to move. In the first infinitesimal fraction of a second after the Big Bang, the entire cosmos was smaller than a proton, yet hotter than a trillion suns. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were not yet distinct, but unified in a symmetry so perfect our mathematics can only approximate it. This is not poetic license. It's the frontier of theoretical physics, where equations break down and our understanding dissolves into speculation. Here's where the mystery deepens. We know the universe is expanding because we can measure it. The cosmic microwave background radiation, the afterglow of the Big Bang itself, surrounds us in all directions like a perfect sphere, with Earth apparently at its center. This creates the illusion that we occupy a special place in the cosmos, that the Big Bang happened here. But we don't, and it didn't. The cosmic microwave background only appears to center on us because light from the early universe has taken the same amount of time to reach us from all directions. If you traveled to the most distant galaxy, we can observe. You would see exactly the same thing. A perfect sphere of radiation with yourself at the center. This uniformity presents a problem. Regions of the cosmic microwave background on opposite sides of the sky are too far apart to have ever been in causal contact. Light, traveling at its immutable cosmic speed limit, could never have carried information between them. Yet, they have precisely the same temperature, down to 1 part in 100,000. It's as if two people on opposite sides of the Earth simultaneously wrote identical novels, word for word, without ever communicating. This is the horizon problem, and it suggests something extraordinary about the shape and early history of our universe. To solve this puzzle, cosmologists proposed cosmic inflation, a period of exponential expansion in the universe's first trillionth of a second, when the cosmos expanded faster than light itself, stretching quantum fluctuations into the seeds of galaxies. Inflation is like taking a wrinkled handkerchief and suddenly stretching it taut. The microscopic variations become macroscopic features, while the overall fabric becomes remarkably flat. This explains the universe's observed uniformity, but it raises as many questions as it answers. If inflation occurred, what caused it? What drove the universe to suddenly expand at such an incomprehensible rate? And what caused it to stop? And, most unsettlingly, inflation may not have been a one-time event. The quantum fields that powered it might still be inflating in regions beyond our cosmic horizon, giving birth to new universes in an eternal process. Bubbles of reality forming in a quantum foam that stretches infinitely in all directions and lasts forever. Now we approach the heart of our mystery. When cosmologists say the universe is flat, they're not referring to a shape like a sheet of paper. They're describing its curvature in four-dimensional spacetime. Einstein showed us that mass curves space, creating gravity. On a cosmic scale, the total mass and energy of the universe determine whether spacetime curves positively like a sphere, negatively like a saddle, or remains perfectly flat. In a positively curved universe, parallel lines eventually converge, and the universe closes in on itself like the surface of a hypersphere, finite yet boundless. If you could travel in a straight line through such a universe, you would eventually return to your starting point from the opposite direction, having circumnavigated reality itself. In a negatively curved universe, parallel lines diverge, and the cosmos opens outward like an infinite saddle. Such a universe would be boundless and infinite, expanding forever into itself, creating ever more space as it grows. But our best measurements suggest a flat universe, one where parallel lines remain parallel forever, where Euclidean geometry holds true on the grandest scales. This flatness is so precise that it defies probability. The universe's curvature is flat to within 0.4% of the critical value. It's like balancing a pencil on its point for 14 billion years without it falling over. This extraordinary fine-tuning demands an explanation. The shape of the universe determines its fate. In a closed universe, gravity eventually halts expansion and pulls everything back together in a big crunch. In an open universe, expansion continues forever, leading to a big freeze as stars burn out and entropy approaches maximum. But our flat universe suggests a third possibility, a perfect balance point between collapse and eternal expansion, except for one crucial detail: dark energy. About 7 billion years ago, something changed. The universe's expansion, which had been slowing due to the gravitational attraction of matter, began to accelerate. Space started stretching faster, pushing galaxies apart with increasing speed. This acceleration requires energy, dark energy, that seems to be inherent to space itself. The more space expands, the more dark energy there is, creating a feedback loop of ever faster expansion. This changes everything about our cosmic future and raises profound questions about cosmic geometry. If space can create more of itself, generating energy in the process, is it truly flat? Or does it possess hidden dimensions or properties we've yet to discover? Consider the ripples in spacetime created by gravitational waves. Distortions so subtle they change distances by less than the width of a proton. These waves, predicted by Einstein and detected a century later, reveal that space isn't just a static stage where cosmic events unfold. It's a dynamic medium that stretches, compresses, and undulates. What else might space be doing that we cannot yet measure? If the universe has no edge, then where does it begin? This isn't just a riddle. It's a fundamental challenge to our conception of reality. A finite universe without boundaries seems impossible to our Earth-evolved intuition. Yet mathematics shows it's not only possible but perhaps necessary. Topology, the mathematical study of shapes preserved under continuous deformations, suggests our universe could have exotic structures beyond simple curvature. It could be shaped like a torus, a donut, where traveling far enough in certain directions brings you back to your starting point. It might possess complex connectedness, with shortcuts through space-time that link distant regions. The cosmos might even have a handedness, a subtle asymmetry that influences the evolution of matter and forces. The universe we observe, the stars and galaxies visible from Earth, is just a bubble of light 93 billion light-years across, centered on us. But this observable universe may be an infinitesimal fraction of what exists. Beyond our cosmic horizon, where light has not yet had time to reach us, the universe continues. How far? Perhaps infinitely. Perhaps it wraps around itself. Perhaps it fragments into a multiverse of divergent realities. The map of existence extends far beyond the territory we can observe. Stranger still is the universe's arrow of time. We experience time as flowing inexorably from past to future. But Einstein showed that time is relative. It flows differently for observers moving at different speeds or in different gravitational fields. Near a black hole's event horizon, time nearly stops relative to distant observers. In the early universe, time and space were so warped by extreme density that they became almost indistinguishable. What does this mean for the shape of a universe where time itself is part of the geometry? These are not just academic questions. Every possibility for the universe's shape carries profound implications for its origin and fate. A closed universe suggests a definite beginning and end. An open universe implies eternal expansion. A flat universe balanced on the knife edge. Between these destinies hints at unseen mechanisms maintaining this precarious equilibrium. And all of this assumes the universe actually exists in the way we think it does, an assumption that quantum mechanics has repeatedly challenged. As we peer deeper into space, we're also looking further back in time. The light from distant galaxies has traveled billions of years to reach our telescopes, bringing images of the cosmos as it was when the Earth was still forming. These ancient photons carry information about the universe's early geometry, before dark energy accelerated its expansion. They tell a story of evolution not just in the universe's contents, but in its fundamental shape, a cosmic architecture that breathes and grows and transforms itself over aeons. And so our search for the true shape of the universe becomes a journey, not just through space, but through time, dimensions, and the very nature of reality itself. Every discovery about our universe's shape reveals a deeper layer of mystery. Imagine yourself standing at the edge of a vast ocean at night. The water stretches beyond sight, merging with darkness at the horizon. You dip your hand in, feeling its substance, measuring its temperature and salinity. But these surface measurements tell you nothing of the abyssal trenches miles below, the underwater mountain ranges, the currents that circulate through the depths like a planet-wide heartbeat. This is our predicament as cosmic cartographers. We sample our universe from a single point in space and time, trying to map an ocean of reality we cannot see in its entirety. Let's begin with what seems like a simple question. What happened? At the exact moment of the Big Bang? The mathematics of general relativity, our most successful theory of gravity and spacetime, points to a singularity, a point of infinite density and zero volume, where the laws of physics break down completely. But modern physics abhors infinities. They're mathematical warning signs, red flags indicating where our theories fail. Quantum mechanics, the physics of the very small, suggests something different. Instead of a singularity, the early universe might have been a quantum foam, a seething landscape of virtual particles and probability waves where space and time themselves became uncertain. In this picture, the universe didn't begin from a point, but emerged from a quantum state where concepts like before and beginning lose their meaning. Imagine reality as a film reel, where time is not flowing, but every moment already exists. The Big Bang isn't the first frame of this cosmic film. It's the boundary beyond which the film becomes too damaged to view. We cannot see past it, not because nothing exists there, but because the information from earlier frames cannot reach us intact. This boundary, The cosmic horizon of our knowledge is not just a limit of observation, but potentially a fundamental feature of reality itself. Some cosmologists now suggest that the Big Bang wasn't the beginning of time, but a phase transition, like water becoming ice, where the universe changed states, perhaps from some unimaginable condition to the expanding spacetime we now inhabit. Loop quantum cosmology, a theory emerging from attempts to merge quantum mechanics with general relativity, proposes something even more radical. Our universe might have collapsed from a previous incarnation, reaching maximum density at the Big Bang before bouncing back into expansion. In this scenario, our universe undergoes cycles of expansion and contraction, with each bang serving as both the end of one cosmic epoch and the beginning of another. The universe becomes not a one-time creation, but a perpetual phoenix, dying and being reborn in an eternal cycle. These theories transform our understanding of cosmic shape. If the universe cycles through contractions and expansions, its geometry must change over time, like a lung breathing in and out on scales of billions or trillions of years. The flat universe we measure today might be merely a phase in a dynamic process, a moment of perfect balance between cosmic inhalation and exhalation. But the mystery deepens when we consider another possibility: the multiverse. Quantum mechanics tells us that particles exist not in definite states, but as probability waves that collapse into specific states only when measured. Some physicists, including Hugh Everett in his many worlds interpretation, suggest that every quantum possibility becomes reality in some universe. Every time a quantum event could go one way or another, reality branches, creating parallel universes that encompass every possible outcome. Inflation theory adds another dimension to this cosmic branching. If the quantum fields that drove cosmic inflation continue inflating in regions beyond our horizon, they create bubble universes that expand into their own spacetimes with potentially different physical laws and dimensions. Our universe would be just one bubble in an infinite cosmic foam, each bubble with its own geometry and physical constants. In this scenario, asking about the shape of the universe becomes like asking about the shape of a single wave in an ocean. It has a local form we can measure, but this form is just a temporary configuration in a much larger, more complex system. The true shape might be that of the multiverse itself, a metacosmic structure beyond our dimensional comprehension. Consider black holes, objects so massive that not even light can escape their gravitational pull. At their centers may lie singularities where space and time curve infinitely. Or perhaps not. Recent theories suggest that matter falling into black holes might emerge in another region of space-time, or even another universe entirely. Black holes could be cosmic tunnels, wormholes connecting different regions of our universe, or bridges to other universes in the multiverse. If our universe is filled with such tunnels, connections that bypass the conventional fabric of space-time, then its topology becomes infinitely complex. Imagine a piece of paper where distant points are connected by folding the paper to bring them together. The shortest distance between two points might not be a straight line, but a shortcut through higher dimensions. Our universe's true shape might include such folds and connections invisible to conventional observation. String theory, an ambitious attempt to unify all forces and particles, suggests that reality consists of tiny vibrating strings in 10 or 11 dimensions. The three spatial dimensions we experience are merely those that expanded during cosmic inflation, while the others remained tightly curled at subatomic scales. If true, our universe isn't just curved in the three dimensions we perceive, but twisted and folded through higher dimensions we cannot directly experience. Imagine an ant walking on a garden hose. To the ant, the hose seems two-dimensional: forward, chart backward, and left, right. The ant cannot perceive that the hose curves through a third dimension. Similarly, we might be moving through a universe that curves through higher dimensions without realizing it. Our cosmic measurements detect only the shadows these higher dimensions cast in our perceivable reality. The holographic principle takes this dimensional mystery further. Inspired by black hole thermodynamics, it suggests that all the information in a volume of space can be encoded on its boundary surface. Just as a two-dimensional hologram can create the illusion of three dimensions, our three-dimensional reality might be encoded on a two-dimensional boundary at the edge of the universe. We would experience three dimensions, but the fundamental reality would be a lower dimensional information structure. This isn't mere speculation. It's supported by the mathematics of string theory and black hole physics. If true, it would mean that the shape of our universe is fundamentally different from what we perceive. The volume of space, with its galaxies and voids, would be a projection of information stored on a distant cosmic surface. Reality would be more like a cosmic computer simulation than the substantial volumetric space we seem to inhabit. These theories reshape our understanding of cosmic geometry in profound ways, but they also raise a troubling question. If our universe might be a holographic projection, a bubble in a multiverse, or a higher dimensional structure beyond our perception, can we ever truly know its shape? Are we like the proverbial blind men touching different parts of an elephant, each convinced we understand the whole based on our limited sample? The challenge becomes even greater when we consider dark matter and dark energy, invisible components that make up 95% of our universe's content. Dark matter binds galaxies together through gravity, despite being undetectable except through its gravitational effects. Dark energy drives the accelerating expansion of space despite having no obvious source. Together, they form an invisible architecture that shapes the visible universe like hidden supports determine the form of a building. Dark energy is particularly mysterious. Its pressure, negative and constant throughout space, suggests it might be an intrinsic property of vacuum itself, a baseline energy inherent to empty space. If so, it connects directly to the cosmological constant Einstein initially included in his equations before removing it, only to have it reinstated by modern observations. This constant, representing the energy density of empty space, determines how quickly the universe expands and, consequently, its large-scale geometry. But why does dark energy have precisely the value we observe? If it were slightly stronger, it would have prevented galaxies from forming. If slightly weaker, the universe would have recollapsed long ago. This extraordinary fine-tuning, along with similar precision in other cosmic parameters, has led some physicists to invoke the anthropic principle. The universe has the properties we observe because only such a universe could produce observers like us to measure those properties. In an infinite multiverse with varying physical constants, most universes would be sterile, unable to form stars, planets, or life. We inevitably find ourselves in one of the rare universes compatible with our existence. This doesn't explain why the physical constants have the values they do, but it explains why we observe these particular values rather than others. This anthropic reasoning transforms our quest for the universe's shape. Perhaps we're asking the wrong question. Instead of, what is the true shape of the universe, we might ask, why do we observe this particular shape among all possibilities? The answer might not lie in physics alone, but in the conditions necessary for observers to evolve and ask such questions. Quantum cosmology suggests something even more radical. The wave function of the universe includes all possible configurations, all possible shapes and histories simultaneously superimposed. The particular universe we observe, with its apparent flatness, accelerating expansion, and specific distribution of matter, might be just one manifestation from this quantum superposition, selected not by some external observer, but by our very act of observation. Imagine reality as a vast mathematical library containing the equations for every possible universe. Most of these universes remain abstract possibilities, mathematical structures that never actualize. But some, through processes we don't yet understand, cross the threshold from possibility to actuality. Our universe might be one such actualized structure, selected from infinite potentialities by principles we're still discovering. This view aligns with a growing perspective among theoretical physicists that reality at its most fundamental level is mathematical, not just described by mathematics, but actually made of it. In this view, the shape of the universe isn't a physical property, but a mathematical one, a particular solution to the equations that govern reality. Max Tegmark's mathematical universe hypothesis proposes that all structures that exist mathematically exist physically. Our universe would be just one structure in a vast landscape of mathematical forms, each with its own physical instantiation somewhere in the multiverse. 3. Familiar dimensions of space and time would be emergent properties of more fundamental mathematical relationships. If reality is fundamentally mathematical, then the true shape of the universe might not be expressible in conventional geometric terms at all. It might be a higher-order mathematical structure that manifests as the space-time we experience. Just as the seemingly solid matter of everyday objects emerges from quantum fields and forces. This brings us to a profound question at the intersection of physics and philosophy. Is the universe discovered or invented? Do our theories reveal pre-existing structures in nature? Or do they construct models that we project onto a reality that might be fundamentally different from anything we can conceive? The physicist Eugene Wigner noted the unreasonable effectiveness of mathematics in describing the physical world. Why should reality conform so precisely to our mathematical models? Perhaps because mathematics isn't just a human tool, but the fundamental language of reality itself. If so, the true shape of the universe might be a mathematical pattern, a set of relationships and symmetries that generates the cosmos we observe. As we reach the frontiers of modern cosmology, we find that our questions about the universe's shape lead to deeper questions about the nature of reality itself. Is space fundamental, or does it emerge from more basic entities? Is time a dimension or a process? Do our familiar concepts of geometry apply at the deepest levels of reality? Or are they approximations valid only at the scales we can perceive? These questions aren't merely academic. They drive the development of new theories and experiments that probe reality at its most fundamental level. The Large Hadron Collider, gravitational wave observatories, and precision measurements of the cosmic microwave background all seek evidence that could resolve these cosmic mysteries. And yet, despite our most sophisticated instruments and theories, the universe keeps its deepest secrets. We map its shape indirectly, like cartographers charting distant shores from fragmentary reports. Each new discovery reveals how much remains unknown, each answered question spawning a dozen more. The quest for the true shape of the universe becomes not just a scientific endeavor, but an odyssey into the limits of human knowledge and imagination. Now we must confront the paradoxes, the cosmic contradictions that emerge when we push our theories to their limits. These aren't mere puzzles awaiting solution, but fundamental tensions in our understanding that may point toward revolutionary new physics. The flatness problem haunts cosmology like a persistent ghost. Our universe is flat to within 0.4% of the critical density, a precision so extreme it defies probability. Imagine balancing a pencil on its point for 14 billion years. The initial conditions of the universe would need fine-tuning to 1 part in 10 to the 62, a number larger than all the particles in the observable universe. Without an explanation for this flatness, cosmologists face an uncomfortable choice: either accept an implausible coincidence or admit our theories are incomplete. Cosmic inflation, the exponential expansion in the universe's first fraction of a second, offers a solution, smoothing out primordial curvature like stretching a wrinkled balloon. But inflation itself requires fine-tuning. What triggered it? What stopped it? And if inflation can happen once, why not multiple times, creating a fractal multiverse of bubble universes with different physical laws? The horizon problem adds another layer of mystery. Regions of the cosmic microwave background on opposite sides of our sky have the same temperature to 1 part in 100,000, despite never having been in causal contact under conventional cosmology. It's as if two people who never communicated somehow wrote identical symphonies, note for note. Either information traveled faster than light in the early universe, or these regions shared an earlier connection our current models don't capture. Then there's the cosmological constant problem, perhaps the greatest quantitative failure in theoretical physics. Quantum field theory predicts that empty space should seethe with virtual particles and fields, creating an energy density 10 to the 120 times larger than what we observe. This discrepancy, 120 orders of magnitude, is so vast it's difficult to comprehend. If theory and observation disagree by a factor of a trillion times, something fundamental is missing from our understanding. These paradoxes aren't just academic curiosities. They strike at the heart of our cosmic models and highlight the provisional nature of scientific knowledge. For all our sophisticated mathematics and precise observations, we might be like ancient astronomers plotting the motions of planets with epicycles. Our models work within limits, but miss the deeper structure of reality. Consider the possibility that our universe exists in higher dimensions we cannot directly perceive. In 1919, mathematician Theodore Kaluza discovered that by adding a 5th dimension to Einstein's equations, he could unify gravity with electromagnetism. Today, string theory suggests our reality might have 10 or 11 dimensions, with the extra dimensions curled up at scales too small to detect. If true, our three-dimensional measurements reveal only the shadow of cosmic geometry, missing its BDE higher dimensional contours. Imagine a flat painting of a garden. To a two-dimensional being living in this painting, reality would seem completely flat. But we, seeing from outside, recognize the garden's three-dimensional nature represented in the painting. Similarly, our universe might be a projection of higher dimensional structures, a possibility that transforms the question of cosmic shape from "what is it?" to "what is it a projection of?" This perspective aligns with another profound paradox. The universe seems simultaneously finite and infinite. We can measure its age, 13.8 billion years, and the radius of our observable portion, 46.5 billion light-years, suggesting finitude. Yet cosmological measurements indicate a flat geometry that extends infinitely in all directions. How can something be both bounded and boundless? The answer might lie in the difference between the observable universe, the portion from which light has had time to reach us, and the entire cosmos beyond our cosmic horizon. If space is indeed infinite, then our observable universe is an infinitesimal fraction of what exists. Like sailors on an ocean who can see only to the horizon, we mistake our visible bubble for the entirety of reality. But an infinite universe raises its own paradoxes. If space extends forever and matter is distributed uniformly on the largest scales, then everything that can happen does happen, not just once, but infinitely many times. In an infinite universe, exact copies of Earth and everyone on it would exist, separated by unimaginable but finite distances. This isn't speculation, but a mathematical consequence of infinity combined with quantum mechanics, which ensures only a finite number of possible particle configurations within any bounded region. The multiverse concept offers a different kind of infinity, not of space within one universe, but of universes themselves. String theory suggests a landscape of possible vacuum states numbering around 10,500, far more than the 1080 atoms in our observable universe. Each vacuum state corresponds to a different universe with its own physical laws, dimensions, and fundamental constants. This cosmic landscape transforms the question of our universe's shape into something more profound. Why does our particular universe have the shape and properties we observe rather than any of the countless other possibilities? The why becomes as important as the what, leading us into realms where physics merges with philosophy. Perhaps the most unsettling paradox emerges from quantum mechanics itself. The Copenhagen interpretation, mainstream for nearly a century, holds that quantum systems exist in superpositions of multiple states until measured when they collapse into specific states. But what constitutes a measurement? And what happens in the early universe when no conscious observers existed to measure anything? The many worlds interpretation offers a radical alternative. Reality never collapses into single states, but branches into parallel universes encompassing all possibilities. If true, the shape of the universe becomes meaningless without specifying which branch of the quantum multiverse we're discussing. Our cosmic geometry would be just one manifestation from an infinite ensemble of equally real geometries. This quantum uncertainty extends to the birth of the cosmos itself. Quantum cosmology suggests that universes can spontaneously emerge from quantum fluctuations in a pre-existing state called the quantum vacuum. Like virtual particles that pop into existence and vanish in empty space, entire universes might bubble up from nothing, governed only by quantum probability. Physicist Alexander Vilenkin describes this as a quantum tunneling from nothing, where nothing isn't empty space, but the absence of space, time, and physical laws altogether. In this picture, our universe isn't shaped like anything we can visualize. It's a quantum probability wave that happened to stabilize into the space-time we inhabit. These theories might seem like science fiction, but they emerge from our most successful physical models pushed to their logical conclusions. They're not wild speculations, but serious attempts to reconcile observations with mathematics, to understand a universe that increasingly appears stranger than we can comprehend. The work of theoretical physicist Juan Maldacena adds another layer to this cosmic puzzle. His anti-de Sitter conformal field theory, AD-S-CFT, correspondence, suggests that a universe with gravity can be exactly equivalent to a quantum theory without gravity in one fewer dimension. This holographic duality implies that our three-dimensional reality might be exactly equivalent to a two-dimensional quantum system at the boundary of space-time. If true, which version is more fundamental? Are we living in a three-dimensional universe that happens to have a two-dimensional description? Or is the two-dimensional system more real, with our familiar dimensions emerging from it? The mathematics works either way, leaving us with a philosophical rather than physical question about the true nature of reality. This duality between descriptions reflects a deeper truth about physics. Our theories don't capture reality itself, but model it from particular perspectives. Just as light can be described as both a wave and a particle depending on the experiment, The universe might have multiple equally valid geometric descriptions, depending on the questions we ask. Physicist Carlo Rovelli's relational quantum mechanics takes this further, suggesting that reality consists not of objects with intrinsic properties, but of interactions between systems. In this view, the universe doesn't have a shape independent of measurement. Its geometry emerges from the network of relationships between its parts, like a social network defined not by individual people, but by their connections. This relational perspective resonates with ancient philosophical traditions. Buddhist emptiness doctrine, shunyata, holds that nothing possesses inherent existence independent of its relationships. Things are empty of intrinsic identity, but full of interconnections. Applied to cosmology, this suggests the universe might not have any intrinsic shape, but acquires geometry through relationships between observer and observed. Modern physics increasingly confirms this view. Quantum entanglement, Einstein's spooky action at a distance, creates correlations between particles that transcend space and time. These quantum connections might be more fundamental than space itself, with three-dimensional reality emerging from networks of entangled quantum information. Physicist Leonard Susskind proposes that space is literally made of entanglement. Quantum connections between microscopic bits of information change the pattern of entanglement, and you change the geometry of space. In this picture, cosmic shape isn't a fixed structure, but an evolving pattern of quantum relationships, constantly shifting as the universe evolves. This information-theoretic approach transforms our cosmic questions. Instead of asking about the universe's shape as a static geometric form, we might ask about its computational structure, the pattern of information processing that generates reality as we experience it. Physicist Seth Lloyd suggests the universe itself might be a quantum computer, performing calculations that manifest as the physical processes we observe. These abstract models converge around a startling possibility. What we call the universe might not be a thing at all, but a process, an ongoing computation or information transformation that generates the appearance of space, time, and matter. Its shape would be the structure of this process, not a static form, but a dynamic pattern evolving through relationships. This view aligns with emerging theories of quantum gravity. Loop quantum gravity represents space not as a continuous medium, but as a network of discrete atoms of spacetime connected by spin networks. These networks constantly evolve, creating the illusion of continuous space and time at larger scales. The universe's shape becomes the macro-scale pattern emerging from this microscopic quantum weave. Similarly, causal set theory suggests space-time consists of discrete events connected by causal relationships, essentially a vast network defining what can affect what. The familiar geometry of relativity emerges statistically from countless such connections, like how temperature emerges from the collective behavior of molecules. The universe's shape becomes a causal structure rather than a geometric one. These theories highlight a profound philosophical insight. What we call reality might be less like a noun and more like a verb, not a static entity, but an ongoing process generating the appearance of objects in space and time. The universe's shape would be the pattern of this process, perceptible to us only through its effects on matter and energy. This process-oriented view resolves certain paradoxes while creating new ones. If reality is fundamentally about relationships, rather than objects, then asking about the universe's true shape, independent of observation, becomes meaningless. Like asking about the sound of one hand clapping. The shape emerges through the act of measurement itself, through the ongoing dialogue between observer and observed. Yet, this raises troubling questions about objectivity. If cosmic geometry depends on perspective, does the universe have any objective properties at all? Or is reality fundamentally subjective, with different observers inhabiting effectively different universes? Quantum mechanics suggests a middle path. Reality consists of objective patterns of possible observations, with each observation actualizing one possibility from this landscape of potentials. The universe's shape would be neither purely objective nor purely subjective, but interactive, a joint creation of cosmos and observer. This interactive model resonates with developments in quantum cosmology. The Wheeler-DeWitt equation, a foundational formula in quantum gravity, describes the entire universe as a wave function evolving not through time, which is part of the system it describes, but through a more abstract configuration space. Time and space, as we experience them, emerge from this more fundamental quantum state. If true, then asking about the universe's shape before the Big Bang or outside our cosmic horizon becomes like asking what's north of the North Pole, a question that assumes a framework, space, time, that doesn't exist in the context being queried. The shape of reality might be more like a narrative structure than a geometric one, with past and future here and there, emerging from a deeper, timeless quantum reality. This timeless perspective appears in the work of physicist Julian Barber, who argues that time is not a fundamental dimension, but emerges from relationships between configurations of the universe. Each now is a complete configuration of reality, with the appearance of time flow arising from correlations between these configurations. The universe's shape would encompass all possible configurations simultaneously, with our experience of a changing cosmos being just one path through this static landscape of possibilities. These theories might seem esoteric, disconnected from observable reality, but they're driven by the need to reconcile quantum mechanics with general relativity. Our two most successful physical theories, each verified to extraordinary precision in its domain, yet fundamentally incompatible with each other. The true shape of the universe must somehow encompass both quantum uncertainty and relativistic space-time curvature, a unified framework we've yet to discover. The search continues with massive experimental efforts. The James Webb Space Telescope peers into cosmic dawn, revealing the universe's earliest structures. Gravitational wave observatories detect ripples in space-time from colliding black holes, providing direct evidence of Einstein's predicted space-time. Geometry. Particle accelerators probe shorter and shorter distances, searching for evidence of extra dimensions or new forces that might reshape our cosmic understanding. Yet for all this effort, the universe guards its deepest secrets. Each new discovery reveals how much remains unknown, each answered question spawning a dozen more. The true shape of reality might lie beyond not just our current knowledge, but our capacity to know. A cosmos not just stranger than we imagine, but stranger than we can imagine. And perhaps this is the universe's greatest paradox. That minds evolved to track predators across savannas can contemplate the shape of all reality. That collections of atoms can wonder about the totality from which they emerged. That the universe has organized part of itself into beings capable of asking these questions at all. In our quest to understand the cosmos, we find that we ourselves, the questioners, are as mysterious as the universe we seek to comprehend. We've been discussing the shape of the universe as if it were something separate from us, a vast structure we inhabit but remain distinct from. But this comfortable separation is an illusion. The truth is far more unsettling. You are not in the universe. You are the universe. A temporary configuration of atoms assembled into consciousness, experiencing itself subjectively for the briefest moment in cosmic time. Every atom in your body was forged in the heart of a dying star. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all created in stellar furnaces that exploded billions of years ago, scattering their elemental remains across space until they eventually coalesced into you. You are not just connected to the cosmos, you are made of it. The universe shaped itself into you so it could contemplate its own existence. And what are you contemplating? A reality so vast that your mind, evolved to track predators across savannas and remember seasonal fruit locations, cannot truly comprehend it. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars. If every star in a single average galaxy represented 1 neuron, you would need 10 million human brains to match the number of stars in the observable universe alone. Yet this observable portion, this bubble of light 93 billion light-years across, may be an infinitesimal fraction of what exists. Beyond our cosmic horizon lie realms we can never see, potentially extending to infinity. If space is truly infinite, then everything that can happen according to the laws of physics does happen. Not just once, but an infinite number of times. Let that sink in. In an infinite universe, there are infinite copies of you reading these exact words right now. Some copies are identical down to the subatomic level. Others differ in ways too subtle to notice. Still others diverge dramatically. Versions of you who made different choices, followed different paths, became different people. These aren't metaphorical possibilities, but actual realities existing in distant regions of an infinite cosmos. If time is an illusion, as both relativity and quantum mechanics suggest, then everything you've ever done and will ever do might exist simultaneously in a 4-dimensional block universe. Your birth, your death, and this moment of realization all exist permanently in different regions of space-time. You're not progressing through time. You're stretched across it, with the illusion of now created by your consciousness as it integrates. Information slice by slice. What if your consciousness itself is more fundamental than the reality it perceives? Some interpretations of quantum mechanics suggest observation plays a crucial role in determining reality. The universe might exist in a superposition of all possible states until measurement collapses these possibilities into specific outcomes. If true, then reality isn't something that exists independently of perception. It's something created through the act of observation itself. Consider this. You've never directly experienced the universe. Everything you've ever known, every sight, sound, taste, touch, and thought, has been a model created by your brain. The colors you see aren't properties of objects, but interpretations of electromagnetic wavelengths. The solidity you feel isn't fundamental, but the repulsion of electron clouds. Your entire perception of reality is a simulation running on the wetware of your brain, approximating an external world you can never directly access. What if the universe is alive, and we are just its fleeting thoughts? Panpsychism, the view that consciousness is fundamental to reality rather than emerging solely from complex brains, has experienced a revival among some theoretical physicists. If consciousness is intrinsic to matter at some basic level, then the cosmos isn't just mindless particles moving according to forces, but something more akin to a vast, thinking entity. We wouldn't be conscious beings in an unconscious universe, but local concentrations of a consciousness that pervades everything. This isn't mere mysticism. Physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff have proposed that quantum processes in neural microtubules might be responsible for consciousness. If quantum effects play a role in mind, then consciousness might be connected to the fundamental quantum field that underlies all reality. Your thoughts would be localized patterns in a universal quantum consciousness that encompasses all existence. The scale of cosmic time is equally shattering to human significance. if the universe continues expanding forever, as current evidence suggests, it faces a future of unimaginable desolation. In about 100 trillion years, all stars will burn out. In 1040 years, all matter will decay into radiation. Eventually, even black holes will evaporate, leaving nothing but an ever-expanding void of dilute radiation barely above absolute zero. Against this temporal canvas, all human history, from the first stone tools to whatever heights our civilization might reach, occurs in the first instant of cosmic time. Everything we've ever built, discovered, loved, or fought for will be erased not just from existence, but from memory. No trace will remain that anything happened at all. The universe forgets. And yet, here you are, a collection of atoms capable of contemplating its own existence, matter that knows its matter, stardust that can wonder about its origins. You exist at the razor's edge of cosmic possibility, in one of the vanishingly few places and times where the universe has organized itself into consciousness. Consider the unlikely accident of your existence. For you to be here, countless specific events had to occur exactly as they did. From the precise pattern of quantum fluctuations in the early universe to the particular sperm and egg that formed you. If any detail had been different, you would never have existed. The probability of your specific consciousness arising is effectively zero. Yet here you are, a statistical impossibility experiencing itself. What does this mean for the shape of the universe? Perhaps we've been asking the wrong question. Instead of, what is the universe's shape? We might ask, what shapes the universe? And one answer might be, perspective. The universe takes different forms depending on how and from where it's observed. There isn't one true shape, but many valid geometries emerging from different reference frames and measurement choices. Maybe you shape the universe as much as it shapes you. Not in the shallow sense of creating your own reality, but in the deeper sense that observation and measurement help determine what aspects of quantum possibility become actualized. The cosmos might be fundamentally participatory, with consciousness not just witnessing reality, but helping to create it through the choices of what to measure and how to interpret those measurements. Or perhaps the universe isn't shaped like anything we can visualize. Our concept of shape itself might be a limited tool evolved for navigating the middle-scale world of terrestrial threats and opportunities. At the cosmic scale, reality might be better described as patterns of information or networks of relationships than as objects with definite boundaries and positions. This possibility connects to humanity's most ancient wisdom traditions. Buddhist emptiness doctrine, shunyata, holds that nothing possesses inherent existence independent of conditions and relationships. The Advaita Vedanta tradition speaks of Brahman, ultimate reality beyond attributes and forms. Indigenous cosmologies around the world emphasize interconnectedness over individuation. Perhaps these intuitions capture something our equations still struggle to formalize. The true horror isn't that the universe is hostile, but that it is indifferent. It exists at scales so vast and operates according to principles so alien to human concerns that our desperate search for meaning might be like ants trying to comprehend nuclear physics. Not just difficult, but potentially outside the parameters of what our minds evolved to process. And yet, in this cosmic indifference lies a strange dignity. We matter precisely because nothing inherently matters. In a universe without intrinsic purpose, we create purpose. In a reality with no built-in meaning, we generate meaning through our choices and relationships. We are the universe experiencing itself, making itself matter through the ephemeral miracle of consciousness. Look at your hands. These collections of atoms, temporarily assembled into the form you call your body, are the universe's way of touching itself. The light entering your eyes is the universe seeing itself. The thoughts forming in your mind are the cosmos contemplating its own existence. You are not separate from the mystery you're trying to solve. You are part of it, a piece of the puzzle, trying to understand the whole. This is the final vertigo, the recognition that the boundary between self and cosmos is illusory. There is no observer separate from the observed. There is just the universe, folded back upon itself in the form of beings who seek to comprehend their own nature. The shape of the universe includes the shape of your mind as it tries to grasp the shape of the universe. The serpent swallows its own tail, and the mystery consumes itself. Throughout our journey, we've explored the universe as if it were a thing, an object with properties we could measure, a shape we could define. We've considered spheres and saddles, toruses and bubbles, fractals and holograms. But what if the most profound truth about the universe isn't its geometry, but something far more fundamental? What if the universe isn't a noun, but a verb? Not a static structure, but a process of becoming. Not an object, but an activity. The difference isn't semantic. It's revolutionary, transforming our entire conception of reality. Consider this. What we call the universe might be a vast computational process, an ongoing calculation that generates space, time, and matter as its output. The cosmos wouldn't be running according to mathematical laws. It would be those mathematical relationships in action. Reality would be less like a place and more like a story still being written, with each moment a calculation that determines the next. This isn't mere speculation. It aligns with quantum mechanics, where reality consists not of definite states, but of probability waves that collapse into specific configurations only when measured. It resonates with general relativity, where space and time themselves become dynamic, warping and flexing in response to matter and energy. It explains why mathematics, a human invention for describing patterns, works so unreasonably well at predicting physical reality. Perhaps math works because reality is mathematical, at its core, not described by mathematics, but constituted by it. Now picture the cosmos not as a vast expanse of space containing galaxies, but as a network of relationships between events. Each interaction between particles, each quantum fluctuation, each collision of galaxies isn't happening within the universe. It is the universe, the process of reality, calculating its next state. Space and time emerge from these relationships rather than containing them, like how wetness emerges from water molecules without any individual molecule being wet. This perspective reveals something shocking. The shape of the universe might be changing not just over billions of years, but moment to moment, reconfiguring itself with each quantum measurement, each causal connection, each observation. The cosmos wouldn't have a single definite shape, but would exist as a superposition of possible geometries, each with its own probability amplitude, constantly evolving as information flows through the cosmic network. Imagine the early universe, not as a singularity exploding outward, but as a quantum computer with minimal memory, suddenly gaining computational resources, expanding its calculations from simple to complex, from undifferentiated potential to the intricate reality we now inhabit. The Big Bang wouldn't be the beginning of the universe, but a phased transition in an eternal computation, a singular moment when the cosmic algorithm changed its approach. This computational universe wouldn't be running on some substrate outside itself. It would be self-calculating, a process generating itself from itself. And this self-referential quality might explain consciousness. Perhaps awareness emerges naturally when a computational process becomes complex enough to model itself, to simulate its own operations and anticipate their results. Your consciousness would be the universe's computation becoming aware of itself, the cosmic process recognizing its own existence. Now, let's pull back further to a truly shocking possibility. What if the universe is already dead, and we are just experiencing its last echoes? This isn't another thought experiment, but a serious proposal by some theoretical physicists. In the far future of an ever-expanding universe, matter will decay, stars will burn out, and even black holes will evaporate, leaving a diffuse soup of elementary particles separated by unimaginable distances. The cosmos will approach a state of maximum entropy, heat, death, where no ordered structures remain and no further work is possible. But quantum mechanics suggests something peculiar about this final state. According to the Boltzmann brain paradox, in a universe approaching equilibrium, random quantum fluctuations become more likely to produce momentary conscious entities, complete with false memories of a complex past, than to produce the entire ordered history that led to those conscious entities. It's statistically more probable for a brain with illusory memories to fluctuate into existence than for an entire universe with billions of years of consistent history to do so. Taken to its logical conclusion, this suggests a disturbing possibility. What if we aren't living at the beginning of cosmic history, watching the universe expand into its future, but are instead quantum fluctuations in the dying moments of an ancient cosmos, experiencing an illusory past that never actually happened? Our memories, our history, our entire perception of an ordered universe with consistent physical laws, all could be statistical flukes in a reality already at or near its end. This doesn't mean the universe isn't real. It means the reality we experience might be less like a continuous history and more like a momentary configuration of information, a pattern briefly assembled from quantum noise, experiencing itself as if it had a past. The universe wouldn't be shaped like anything. It would be shaped like everything, simultaneously, with our experience being just one possible configuration momentarily realized from infinite potential states. Picture all of space-time, past, present, and future, as a vast crystal, with each point representing a possible configuration of the universe. Most of this crystal consists of high-entropy, disordered states, the quantum static of a dead universe. But scattered throughout this crystal are islands of order, moments of structure and pattern that experience themselves as consistent realities with apparent histories and futures. We might be living not in the actual history of the cosmos, but in one such island of apparent order, a momentary eddy in the entropic flow of an already ancient universe. If this seems too abstract, visualize a dying star. For billions of years, it burns steadily, converting matter to energy in a predictable, orderly process. But in its final moments, it explodes in a supernova, a catastrophic release of energy that, for a brief instant, outshines entire galaxies. In a universe approaching heat death, consciousness might be like these supernovae, final, brilliant flashes of complexity emerging from an increasingly disordered system, moments of profound pattern briefly assembled from cosmic static before dissolving back into randomness. Watch a galaxy spiral through space, its arms sweeping through millions of light years, stars being born and dying in cosmic rhythms that repeat for billions of years. Then realize this majestic structure might be not the foundation of reality, but its last gasp, a pattern briefly assembled from quantum fluctuations in a universe already near its end, experienced as if it had always existed and would continue to exist long after we're gone. Such a universe would have no definite shape because it would have all possible shapes simultaneously, with our experience being just one perspective on this infinite ensemble. The cosmic geometry we measure wouldn't be a property of reality, but a property of our particular vantage point within it, like mistaking the view from a single window for the entire landscape. Yet even this vertigo-inducing possibility doesn't diminish the wonder of existence. If anything, it makes consciousness even more precious, a miraculous assembly of pattern and meaning from chaos, a brief moment when the universe experiences itself as ordered, beautiful, and comprehensible, whether that experience is embedded in a continuous history or a momentary fluctuation. Look out at the night sky. The stars you see might be illusions, not in the sense of hallucinations, but in the deeper sense that the past they seem to represent might never have occurred as we experience it. The light reaching your eyes might be not the residue of actual stars, but the implication of stars, the pattern that must exist in your experience for your conscious moment to maintain its internal coherence. And yet, when you look at those stars, something real is happening. The universe, whatever its true nature, is experiencing itself through your consciousness. Something is aware of something else. Information is being processed. Reality is happening, even if not in the form we instinctively assume. If the universe is infinite, then somewhere out there, another version of you is watching this same cosmic drama unfold, thinking these same thoughts, reaching these same conclusions. And in yet another region, a slightly different you is coming to slightly different realizations. And in countless others, profoundly different versions of you are living lives you cannot imagine, in universes with physical laws and geometries beyond your comprehension. But here, now, in this moment of awareness, whether it's embedded in a continuous cosmic history or a momentary quantum fluctuation in a dead universe, you exist. The universe has shaped itself into an entity capable of contemplating its own nature. Matter has arranged itself into consciousness. The cosmos has grown eyes to see itself, a mind to know itself, and a heart to feel itself. And perhaps that's the most profound truth about the shape of the universe. It's shaped exactly like this moment of understanding, this flash of awareness in which something knows itself. Everything else, the galaxies and quantum fields, the curvature of space-time and the flow of entropy, might be just the scaffolding necessary for this miracle of consciousness to occur, for the universe to experience itself, however briefly, as something rather than nothing. We began our journey with a deceptively simple question. What is the true shape of the universe? But like all profound inquiries, this question has led us not to a single answer, but to ever deeper mysteries. We've traversed cosmic inflation and quantum fluctuations, explored higher dimensions and holographic projections, contemplated eternal expansion and heat death. Yet for all our scientific progress, the ultimate geometry of reality remains tantalizingly beyond our grasp. Not because we haven't looked hard enough, but because the answer may transcend the very concepts we use to frame the question. The universe we've discovered is not the universe our ancestors imagined. It's not a dome above the Earth or a series of perfect crystalline spheres. It's not even the static, eternal backdrop Newton envisioned. Instead, we've found a cosmos that expands and evolves, that curves and warps in response to matter and energy, that might have begun in a flash of inflation and might end in a state of maximum entropy or perpetual expansion. We've found a reality where time and space themselves are not the absolutes they appear to be, but dynamic aspects of a four-dimensional continuum. We've found a universe that might be flat or curved, finite or infinite, singular or multiple. But perhaps the most remarkable discovery isn't about the universe itself, but about our relationship to it. We are not separate observers standing apart from cosmic processes, but expressions of those processes, arrangements of atoms and energy, fields that have become complex enough to contemplate their own nature. The forces that move galaxies move through us. The quantum fields that permeate space constitute our bodies. The arrow of time that carries the cosmos from past to future carries our consciousness from moment to moment. This intimate connection between observer and observed transforms our quest. We're not just asking about the shape of something external to us, but about the shape of a reality that includes us. That is us, in a profound sense. The cosmologist looking through a telescope at distant galaxies is the universe looking at itself. The mathematician writing equations to describe cosmic geometry is the universe describing itself. The child gazing up at the night sky in wonder is the universe wondering about itself. What does this mean for our original question? Perhaps the true shape of the universe includes the shape of the mind that contemplates it. Perhaps reality has a participatory aspect, existing not just as an external structure, but as a dialogue between observer and observed. Perhaps the cosmos completes itself through being known, achieving a kind of closure through the awareness of beings evolved within. Consider this chilling possibility. What if the universe has spent 13.8 billion years evolving precisely so it could know itself through conscious beings? What if the emergence of awareness isn't a side effect of cosmic evolution, but its purpose? Not in the sense of a divine plan or intelligent design, but as an inherent tendency of complex systems to generate ever greater complexity until consciousness naturally emerges. The universe would be shaped not just by forces and fields, but by its own self-realization through minds like yours. This isn't mysticism, but a perspective emerging from the frontiers of physics and complexity theory. Systems theorists speak of autopoiesis, the capacity of complex systems to maintain and reproduce themselves. Quantum physicists discuss measurement and observation as fundamental to reality, not just to our knowledge of it. Information theorists propose that information might be as fundamental as energy or matter. Together, these perspectives suggest a universe that isn't just existing but happening. A cosmic process generating patterns of increasing complexity, with consciousness representing a particular kind of pattern within this process. But here's where the true mystery deepens. If consciousness is the universe knowing itself, then what is the universe? Not just the matter and energy we can detect, not just the space-time we can measure, but the deeper reality that gives rise to these phenomena. What is the substrate of existence? What is the ultimate nature of the stuff that configures itself into stars and planets, fields and forces, brains and minds? What is it that shapes itself into the forms we experience, and that experiences itself through us? These questions may seem abstract, but they have profound implications. If we take seriously the possibility that consciousness isn't just an epiphenomenon of brain activity, but a fundamental aspect of reality, then the divide between mind and matter, between subject and object, begins to dissolve. The universe doesn't just have a physical shape, but a mental one as well, or perhaps more accurately, a psychophysical nature that encompasses both the objective patterns we measure and the subjective experiences we have. This doesn't mean the cosmos is alive or conscious in the way humans are, but it might mean that what we call consciousness is a localized expression of something intrinsic to reality itself, not supernatural but deeply natural, a property of existence that manifests in particular ways when matter organizes into certain patterns. Your awareness would be not something added to the universe, but something the universe does when organized as you. As we reach the limits of what science can currently tell us, we find ourselves at the boundary between knowledge and mystery. But this boundary isn't a wall, it's a horizon, constantly receding as we advance, revealing new landscapes of possibility with each step forward. The questions that seem unanswerable today may find resolution in tomorrow's discoveries, only to give rise to deeper questions that we cannot yet even formulate. This is the glory of the cosmic quest. Not that it leads to final answers, but that it continues unfolding, revealing layer after layer of reality without exhausting its mysteries. The universe doesn't just exist, it happens, it unfolds, it becomes, and so does our understanding of it. What can you do with these insights? How can you participate in this grand cosmic inquiry? First, stay curious. The universe has spent billions of years evolving systems complex enough to wonder about it. Your consciousness represents one of reality's greatest achievements. Your questions, your wonder, your awe are not separate from cosmic processes, but expressions of them. When you look up at the night sky and feel a sense of mystery, that's not just you responding to the universe. It's the universe experiencing itself through you. Second, recognize that science isn't just for scientists. Every time you learn about cosmic inflation or quantum mechanics, every time you contemplate the possibility of higher dimensions or parallel universes, you're participating in humanity's collective effort to map reality. You're helping to shape the mental models our species uses to understand existence. Your understanding may not change the physical universe, but it changes the universe of meaning we collectively inhabit. Third, share these questions with others. The cosmic mystery isn't just an intellectual puzzle, but a source of connection. When you discuss the nature of time with a friend, when you explain the expanding universe to a child, when you debate the multiverse with a colleague, you're not just exchanging information. You're participating in reality's ongoing conversation with itself. You're helping consciousness do what it does best: expand, connect, and complexify. Finally, remember that the greatest mysteries lie not just in distant galaxies, but in everyday experience. The fact that anything exists at all. The fact that mathematical laws seem to govern physical processes. The fact that matter can organize itself into systems complex enough to contemplate their own existence. The fact that you, reading these words right now, are the universe aware of itself. These aren't just scientific puzzles, but existential ones that touch the core of what it means to be conscious in a cosmos that somehow gave rise to consciousness. As our journey comes to a close, we've traveled from the Big Bang to quantum fluctuations, from cosmic inflation to heat death, from multiple dimensions to parallel universes. We've considered a cosmos that might be shaped like a sphere, a saddle, or a torus, or that might transcend geometric description altogether, existing as process rather than structure, as relationship rather than object, as becoming rather than being. And through it all, one truth has emerged. The shape of the universe includes you, not just as an observer standing apart from cosmic processes, but as an expression of those processes, a particular pattern in spacetime where the universe has organized itself into awareness. The light from distant galaxies doesn't just enter your eyes. It becomes part of your experience, part of your memory, part of your understanding. The cosmos doesn't just exist externally. It exists through you, as you. Perhaps this is the most profound answer to our initial question. The true shape of the universe isn't just curved or flat, finite or infinite. It's conscious. Not in some mystical sense, but in the concrete reality. That consciousness has emerged within it. That matter has organized itself into minds capable of mapping reality. That the cosmos has evolved systems complex enough to model themselves and their environment. What will be the next chapter in this cosmic story? What new dimensions of reality will future generations discover? What aspects of the universe remain completely beyond our current imagination? The journey of understanding has no final destination, no point at which we can say, "Now we know everything." Each discovery reveals new mysteries. Each answer spawns new questions. Each horizon reached shows further horizons beyond. And perhaps that's the most wondrous shape of all, an open-ended narrative of discovery that stretches endlessly before us, offering infinite possibilities for deepening our relationship with reality. The universe may be 13.8 billion years old, but in a sense, it's just beginning, continuing to evolve not just physically, but conceptually, taking new forms in the understanding of conscious beings who themselves evolve and develop new ways of knowing. The universe has no conclusion, but neither does your exploration of it. When you gaze at the stars tonight, remember, you're not just looking at the cosmos. You're the cosmos looking at itself. The mystery doesn't exist separately from you, but through you. You are how the universe shapes itself into wonder. We began by asking about the true shape of the universe. We end with a deeper recognition. The universe shapes itself into the question, and into whatever answering understanding we may find. It curves not just through space and time, but through consciousness itself. The cosmos may or may not be infinite, but the journey to understand it, that has no end.